when you have an autonomous differential equation, basically the equation looks like dy dx is a function of y only. Okay? So the important thing is that the right-hand side is a function only of the dependent variable. Okay? Now again, it does have to be dy dx is a function of y. If I'm doing something like my unknown is q and t is time, maybe it's dq dt is an arbitrary function of q. Okay? So remember, these are only symbols. The important thing that you should say in words that what makes a differential equation autonomous, if its derivative is a function only of the dependent variable. The independent variable x does not occur here at all. Okay? We had an example right before. Dy dx equals sine y, that's autonomous. Okay? Because, matter of fact, let me just remind you, right? So dy dx equals sine y, that's autonomous. Because the derivative is only a function of the dependent variable. But the other equation that we had, dy dx equals 0.2 xy, not autonomous, right? Why? Because the right-hand side depends upon x explicitly. You know, very explicitly. Okay. Now I'm going to make a very simple observation over here. Again, our prototype will be dy dx equals f of y. Okay? Suppose I look at the function f of y and I just solve f of y equals 0. Right? Depending, maybe f of y is a quadratic, maybe it's a polynomial, and I'll need some, MATLAB software. Or maybe it's a more complicated function of y. But certainly if you give me function f of y, I can at least numerically find the roots f of y equal to 0. Okay? So solve f of y equals 0. So let the roots be, let's say y1, y2, down to y sub n. These will be numbers, right? Okay. What comes out is that those numbers, y1, y2, yn, think of it as functions, they're constant functions, are actually solutions of the differential equation. Okay? Claim y of x equals yi for any of those guys, okay, is a solution. Of differential equation. How can I prove that? Very simple. The differential equation is dy dx equals f of y. Okay? What happens when I plug in on both sides y of x equals yi, which is a constant? On the left-hand side, I got t by dx of yi, which is 0, right? And that equals f of yi by definition, right? So for example, if one of the roots of fy equals 0, y equals 7, then y equals 7 is a solution of the differential equation. Okay? It's not too interesting because it's a constant, but it actually has a lot of importance and significance, as we'll see. Okay? So these functions that make fy equal to 0, they're called by different people, they're called sometimes equilibrium solutions. And you can see why they're equilibrium solutions, because they don't change with x, right? If the independent variable is time, they're steady, right? So they're called equilibrium solutions. Sometimes they're called stationary solutions. These are just different terminology you'll find. I think there's one more piece of vocabulary that people use. Okay. Or sometimes these guys are called critical points. y1, y2, critical points. Okay? All these different terms are basically characterizing the solutions of f of y equal to 0. Okay. Now I'm going to do, let's just consider the case where there was, say, I think, what do I have here? 2 critical points, okay? Because I don't want to do the most general thing, and you'll see from considering 2 critical points, you'll know how to generalize. Suppose f of y is equal to 0 for y equals y1 and y equals y2. It only has 2 roots, let's say, and y equals y sub 2. Okay, so we got a system now. Remember, we have dy dx equals f of y. That's our starting point. We solve for f of y equal to 0. Suppose this thing only had two roots, y1 and y2. Okay? Here's what we're going to do. I'm going to show you. It's amazing how much information you get just from these equilibrium solutions. Here's the xy region. Okay? Let's call it C1, C2. Okay? So you realize that they're constants. Okay? C1, C2. Okay? The first thing that we're going to do is graph these equilibrium solutions. Let's put them with dashed lines over here. Okay? So here's one of them. That's y equals C2. Right? It's a horizontal line. Right? Y equals 4 or something. And again, I'm assuming here C1, C2 are positive. It doesn't make a difference, right? If it was negative, it would go down there. Let's draw the other one over here where y equals C1. Y equals C1. Obviously, I'm assuming that C1 and C2 are positive for this particular case, and that C1 is less than C2. But the general procedure will be exactly the same, regardless of what the particular values are. Okay. Now, what's going to happen is that I'm going to divide the whole xy plane into 3 regions. We'll call R3 all the points above the second equilibrium solution, y equals C2. We'll let R2, let me put them over here, okay? Then R2, that will be the whole xy plane, that strip between the two equilibrium solutions, C1 and C2. And then finally, there's this region R3, which is everything in the xy plane below the equilibrium solution. And you can see these 3 regions cover the entire xy plane, right? Here you're above C2, here you're between C1 and C2, here you're below C1, okay? I'm going to show you that we can graph solution curves in any of those regions. Yeah?
Would that be region 1 at the bottom?
Huh? Oh, yeah, region 1, thanks. Yeah. Again, I'm the same one. Okay. Now, what we're going to do is the following, okay? Let's say, let's go to x equal to 0, okay? It doesn't have to be. Suppose our initial condition is over there. Here's y. And now I'm going to basically take an initial point, which is, say, over here. Okay? Let's look at a point over there. That's a point in R3. Okay? So long as it's above the second equilibrium solution. Okay. Remember, you have dy dx equals f of y. F of y, you know, that's the slope. Okay? So, given the point, okay, over here, which is in this region, I can calculate, remember I know the coordinates of this point, maybe it's 0, 8, okay, it's above C2. I can go over here and calculate f of y at that point. I know the slope over there, okay? It's either going to be positive or negative. Let's assume, for argument's sake, that it's positive, okay? In any particular case, you'll know what it is. So it has a positive slope, let's say, over there, okay? Now, what's going to happen is we know what the curve looks like right at that point. We have that little red dash. The question is, what happens when I go to the right and to the left? Okay? The beauty of this thing is that you've located all the points where dy dx goes to 0, right? Here, dy dx is positive, okay? So it's going to increase, 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 increase. Now, can it ever decrease? No, because if it decreased, the slope would go from plus to minus. It's continuous. The function goes from plus to minus, it has to go through 0. And there is no 0 over there. These 2 red dashed curves, lines rather, are the only points where f of y is equal to 0, or you have a 0 slope. Okay? So, we go above this point over here, let's say the slope is positive. The thing basically cannot oscillate, it'll just keep growing and growing. Okay? So I should draw something like this. So the solution curve is growing and growing. Now, the problem is though, with this technique, is that you can definitely say, basically, that in this region, as x goes, as we go more and more x, y goes to plus infinity. But 2 things can happen. I can have y going to infinity and x going to infinity. It could just keep going and going and going. Or there could possibly be a vertical asymptote over there. Okay? This analysis doesn't tell you that. It does say, though, basically, that as you go over here, you get higher and higher y, and it never comes down again. It doesn't oscillate. It can't. Okay. Yeah.
Is it possible for, on the left side, if the line were to continue to go to the left side?
We're going to do that right now. Okay. Now, as he said, let's continue to the left. Okay. Okay. So the function increases as a positive slope over here. So we go to the left, it has to fall. It keeps falling, keep falling. Okay. Can it fall and rise again? No, because if it falls and rise, the slope would change sign, it would be 0, and it doesn't happen. So it falls and it falls, right? Now here's the critical thing. What happens is that the question is, can it go into R2? Does it ever cross that red line? And the answer is no. Why? Because of existence uniqueness, okay? All the problems that we're going to do, they're applied problems, the solution existence unique. If we continue this black curve and it crossed that equilibrium solution, okay, you'd have two distinct solutions at a given point. The solution would be non-unique, okay? So what we find is that when you're in one of these strips, let's say, in this case above y equals C2, the slope is of one sign. I just assumed it was positive to be negative, okay? The important thing, it doesn't change. You calculate what it is at this point, arguments say it's positive throughout that strip, okay? And furthermore, when it basically goes to the left, we know we have to decrease. That's not really a really nice smooth curve. I'm trying to draw this as best I can, okay? So it decreases as we go to the left, right? And it asymptotes to y equals C2, to y equals C2, yes. Does not cross, because otherwise we destroy existence uniqueness, okay? So we definitely can say that the limit of y of x in this region, if your integral curve was here based upon this initial condition, then the limit of y of x as x goes to minus infinity actually is C2, right? This asymptotes to C2. Over here, it's going to go to infinity, and we don't know, maybe it's x goes to infinity, y goes to infinity, or maybe there's a vertical asymptote, and we'll see some examples of that, okay? But to the left, we know exactly what happens, okay? Let's go now and do the same thing over here. Let's take a point over here, okay? Take our initial point to be over there, okay? So now I'm taking an initial point between C1 and C2, okay? Okay, you calculate the slope at that point, okay? Calculate the slope at that point, okay. Let's assume that the slope at that point is negative, okay? So we draw a little, I'm going to do, it's negative over here, let's say, okay. It's negative there, it's negative in the vicinity of that point. Okay, so we start our curve, it's basically falling over here, right? Can it rise again? No, because if it went from a negative slope to a positive slope, it oscillated, it would have to go to 0 slope. And the only points of 0 slope are these two red lines. So again, in that strip, as we go to the right, basically it would just keep going. And again, because of uniqueness, it would asymptote to that equilibrium solution. It couldn't cross into the other region. Otherwise, you have two different solutions at the same point. Okay? And again, I assumed over here that the slope was negative, right? In a real problem, you'll know f of y, and you'll be able to determine unambiguously, is it a positive slope here or a negative slope? Same thing over here. But this is giving an illustration over here. Let's suppose that over here, the slope, you take your initial point, and the slope over there is negative. Well, conversely, therefore, if it's a negative slope, as we proceed from this point to the left, the function increases, right? Increases, but can't go into the next region for the same reason. Has to stay in the strip. So it looks like that. Well, that's pretty cool. What it says is that if you take any initial point between the two equilibrium solutions, y equals C1 and y equals C2, okay, it asymptotes to C1 as x goes to plus infinity, asymptotes to C2 as x goes to minus infinity. Okay, so right there, so the positive slope and negative slope doesn't make a difference over here. Let's assume basically positive slope over here, okay? Suppose it's a positive slope over here. Okay, we know what happens. Positive slope increases, okay? Again, can't oscillate, because if it has a positive slope here and it went, say something, suppose it went like this and it went like that, negative slope, no, because then the slope would be 0, and the only place it's 0 slope are the red lines, okay? So we have this, okay, and then of course, it just keeps going, decreasing. Now again, for this curve that I drew, yes, as x goes to, it has a positive slope at this point, it has to asymptote to C1 as x goes to infinity. So solution curve through this point has the behavior that as x goes to infinity, it approaches C1 from below, okay? As you go to the left, it's going to get more and more negative, but we don't know, does it keep going as x goes to minus infinity, does y go to minus infinity? Or maybe there's a vertical asymptote over here, and therefore it goes like this. Okay, we don't know. Okay, but definitely we know that in this region, y is going to go to minus infinity somehow. Okay, and basically what you have there is you have basically sketches of the integral curves themselves, not just the arrows, no computer, okay, based upon just getting the equilibrium solutions and looking at a representative point in each of the regions, okay? And that's and we'll do some problems right now, but that's the general procedure, okay? So again, remember this only applies to autonomous equations. So you have dy dx is equal to f of y, right? The first thing you do is you determine equilibrium solutions or stationary points or critical points, okay? Draw your dashed lines over there, okay? And then, depending upon how many there may be 3 of them, that will divide the region, the whole xy plane, into a distinct number of regions between the equilibrium solutions above and below, etc. Okay? And what we know is that in any of these strips, the slope must be of the same sign, SIGN, throughout. Well, compute it, okay? Take x equal to 0, y equals whatever the number is, as long as it's bigger than C2. Okay, let's assume it's positive. You then just can draw the curve like that. Because what we observe is that as we continue the curves to the right and to the left, they can't migrate into the other region. Because if we do that, we violate uniqueness, and all these problems have unique solutions. Okay? So, I think the one actually I want to do is the dy dx equals sine y, because we have a picture of that one. Okay? Yeah. Now remember the dy, I'm going to show you again the picture that we had. Remember I did dy dx equals sine y. I did the initial value problem. I showed you the direction field. I even showed you that red curve, which is an integral curve. Okay? Let me show you how you can get that using this type of analysis, because it is an autonomous equation. Okay?
In real world, what would be an example of?
Oh, there's plenty of population growth. If you look in the book, they have nice examples of autonomous equations. Matter of fact, all the examples that I did, the cable, the one, the Newton's law of cooling, they were all autonomous, it comes out. If you look at them, it's always a function of the dependent variable. The independent variable doesn't occur explicitly. Okay. So let's do this first example over here. Example 1. Okay, we've seen a picture of that already. Okay, dy dx is equal to the sine